Chapter 12 Atmospheric Hydrology, Section 12.1 Atmospheric Humidity. So humidity is a general term used to describe the amount of water vapor held in air. So we're talking about water in the form of a gas. There are a number of different measures used to determine atmospheric humidity. We're going to look at three different measures. We're going to look at something called a mixing ratio, saturation mixing ratio, and relative humidity. So mixing ratio is defined as the mass of a specific gas component, in this case water vapor, relative to the mass of the remaining gaseous components for a sample of air. So that would include the nitrogen and the carbon dioxide and the oxygen in the air. For measurements of atmospheric humidity, the units used for mixing ratio are grams of water vapor per kilogram of dry air. Saturation mixing ratio is defined as the mass of water vapor that can be held in a kilogram of dry air at saturation. So no more water vapor can be put into this mass of air. It's as full as it can be. Saturation is a condition where any addition of water vapor to this mass leads to condensation of liquid or the deposition of ice at a given temperature and atmospheric pressure. So those last two comments suggest that both mixing ratio and saturation mixing ratio are influenced by temperature and by atmospheric pressure. So let's look at the effect of temperature on saturation mixing ratio. So the following table suggests that the amount of water vapor that can be held in dry air increases with temperature. More importantly, it suggests that this increase is not linear. It is exponential. So what is described here are increases in temperature in an order at a level of 10 degrees Celsius. So we're going from 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50. And you'll note that the amount of water vapor that can be held is not increasing in a linear fashion. So there's roughly a 4 gram increase from 0 to 10. From 10 to 20, it's in the order of 7 grams. From 20 to 30, almost 13 grams. So it's increasing exponentially. Now, relative humidity is the measure that we commonly see on the weather network or in weather forecasts. And relative humidity is tricky because it relies on temperature. It's a relative measure. Relative humidity can be simply defined as the amount of water in the air relative to saturation amount the air can hold at a given temperature multiplied by 100. So in a mass of air, the relative humidity is a function of temperature. On the left-hand side, we see that we have a mass of air at 10 degrees Celsius, and at 10 degrees Celsius, it is at saturation, or 100% relative humidity. If we raise the temperature of that air mass, not adding or taking away any water vapor, what happens is relative humidity starts dropping. And it's dropping because the air has the ability to hold more moisture as it warms up. So from 10 to 20 degrees, we go from 100% relative humidity to 52% relative humidity, increase it another 10 degrees to 30 degrees Celsius, and relative humidity drops even further to 28%, indicating that a lot more water vapor can be held. And this is the reason why we often see dew or frost form in the early morning. That's when temperatures are the coolest, during the day, and what we have is relative humidity might have been during the day, the previous day, 40%. As that air mass cools, the relative humidity increases until either until saturation is reached or deposition is reached, and we get the formation of dew or frost. So let's look at the two concepts of dew point and frost point. So dew point or frost point is the temperature at which a water vapor saturates from an air mass into liquid or solid, usually forming rain, snow, frost, or dew. So rain or snow, that's associated with clouds. Frost or dew, we're talking about what's occurring at the Earth's surface without clouds. Dew point normally occurs when a mass of air has a relative humidity of 100%. This happens in the atmosphere as a result of cooling through a number of different processes. So cooling could be just a radiation loss causing the cooling overnight, or cooling could be caused because the air is being lifted orographically over a mountain. So here's a nice image of frost on blades of grass. So what must have occurred in this image? This was an early morning image. Overnight, temperatures cooled until 100% relative humidity was reached, and the temperature was below zero. So the water deposited on the edges of these leaves as frost crystals, as ice crystals. So how do we measure relative humidity or humidity? Humidity can be measured using several different instruments. Relative humidity is often determined either by a sling psychrometer or a hair hygrometer. A sling psychrometer is a device that consists of two thermometers joined to a piece of plastic or metal. But one thermometer is a little bit different than the other. One thermometer has a woolen sock pulled over the bulb, and that sock is wet. So water is applied to it to make it damp. When you swing this sling psychrometer around like you were in a party, the wet sock starts evaporating water, taking away heat energy from the bulb where the mercury is being held. So the temperature starts dropping in that thermometer, in what's called the wet bulb thermometer. The dry bulb thermometer, temperature doesn't change. It will be the air temperature, but in the wet bulb thermometer, it's going to drop because energy is being lost due to the evaporation of water. If we had 100% relative humidity in the air, both thermometers would have the same temperature. The drier the air is, the lower the relative humidity, the bigger the temperature change will be in that wet bulb thermometer. And it's constant. So we can create psychrometric tables to allow us to measure what is relative humidity depending upon air temperature and the drop of the temperature in that wet bulb thermometer. Hair hygrometers work based on the fact that hair changes its length when humidity varies. Hair is longer when humidity is high or when it's damp. You may have noticed that when you get a haircut. The hair hygrometers either use human or horse hairs, and these hairs are connected to a mechanical lever system. When humidity increases, the length of the hairs becomes longer. This change in length is then transmitted and magnified by a lever system, and there's a scale that shows the relative humidity. In the last 2 decades, satellites have been playing an important role in measuring humidity in the Earth's atmosphere, and this is important for weather forecasting. The GOES satellite has sensors that can detect water vapor in the atmosphere, and it detects it in a layer from 4 kilometers to 12 kilometers above the Earth's surface. This information is very useful in the development of weather forecasts. So you can see whether or not an air mass contains a lot of water vapor, and therefore it's going to produce a lot of precipitation. Another satellite that measures humidity is NASA's Aqua satellite, and it uses a sensor called AIRS to produce 3D maps of water vapor. So here is an image of water vapor as measured by the GOES satellite. So these are the common weather satellites that provide information to meteorologists. Black areas indicate lack of moisture. White areas indicate high moisture. And of course, it's a scale, black to gray to white. So in here we can see a bunch of small systems, probably thunderstorms, having a lot of moisture content associated with them near the tropics and along the, there's a couple along the east coast. Very useful, and these satellite measurements are sort of instantaneous. Here we see global humidity measurements average for a month using the AIRS sensor in the Aqua satellite. So this is the average amount of moisture in the air for January 2003, and it's measured in millimeters of precipitable water, water that could precipitate out. And as we would expect, the highest amount of water vapor in our atmosphere is near the equator. It decreases with latitude, and this is primarily caused by cooling temperatures. Of course, colder air can hold less moisture than warmer air. Here is the same measurement from the same satellite. This time it's July 2003, and we can see moisture has moved into the northern hemisphere as temperatures warm up during the summer season. We can see that there are some areas where moisture is low over the Rocky Mountains because of altitude, over the Himalayas, once again due to altitude and altitude's effect on temperature. Notice how moist India is. So this is the monsoon season. There's a lot of moisture in the air, and a lot of thunderstorms occurring, especially along the edge of the Himalayas. Here is an animation of precipitable water for the year 2016 from the Aqua satellite. Notice the swirling masses of moisture. So we're either looking at mid-latitude cyclones or hurricanes. And of course, notice that the moisture is highest near the equator and decreases with latitude. Very little moisture at the top of the North Pole and the South Pole. And those swirling masses you can see in the Atlantic, those are mid-latitude cyclones. Notice where they get their moisture from originally. It's coming from the Gulf of Mexico. Now we can see the North Pacific Ocean basin. Oh, you can see some hurricanes coming off of Central America, just off the coast of Central America. And we can see mid-latitude cyclones. We can see the moisture is occurring from the ocean just to the east of Southeast Asia and flowing into North America. Here is another animation of atmospheric water vapor from satellite data that focuses on the Pacific Ocean and the western side of North America. Oh, there's a mid-latitude cyclone beginning to form. Now, water vapor in the atmosphere does condense out or freeze out. So let's describe those processes. So there are three processes that create water droplets and ice crystals. And of course, water droplets and ice crystals are the basis of clouds and the basis of precipitation. Condensation is a term that's used to define water moving from vapor to a liquid state. Freezing is water moving from a liquid to solid state, and deposition is moving from vapor to solid, bypassing the liquid state. Now, in the atmosphere, for ice crystals and water droplets to form, they need a surface to precipitate on. Of course, this occurs when water is cooled. So cooling reduces the relative humidity or increases the relative humidity, and saturation occurs at 100%. So both 100% is needed to reach the dew point or the frost point, and then we get the formation of water droplets and ice crystals. And as I said, for water droplets and ice crystals to form, we need a surface, and these surfaces are minute little particles that normally occur in the atmosphere. For condensation to occur, we need particles called condensation nuclei. They're microscopic particles of dust, smoke, and salt. For a snowflake or ice crystals to form, it needs a special type of particle. The particle has to have 6 sides to it, which makes sense when you think of the 6 sides associated with a snowflake. So deposition nuclei are different than condensation nuclei. Sometimes the atmosphere can have not enough nuclei, and we can get a condition called supersaturation. Supersaturation can create relative humidities higher than 100%. So the last point related to this lecture is just keep in mind that condensation, freezing, or deposition can only occur with a relative humidity that is 100% or greater.